Hello everyone. So in this video I'm going to be going over the algorithm known as Dbscan, and that's called Density-Based Spatial Clustering of Applications with Noise. So essentially what this means is, let's break it down. Density-based basically just means the more dense something is, or let me rephrase that, if something is dense, then it is in a cluster. The rest of this, the scan part of this acronym, basically just means it's going to ignore outlier points. So these points I'm drawing right now that don't really belong to a cluster. There's kind of a cluster here, there's kind of a weird shaped cluster here, and there's a kind of a cluster here. These are the three clusters we're looking for, and these are clusters that Dbscan can identify. So now if you look in the bottom left, I've said min PTS equals 3. So what min PTS is representing is the minimum number of points that are going to be inside of a radius epsilon. So what that's going to look like is for any given point, there is a circle of radius epsilon drawn around it. Actually, let me get a different brush size for that. Okay, there's going to be a radius size epsilon, let's call that 5, drawn around it. Now, the minimum number of points is just the number of points also in that circle. So let's just say I add 3 points. So there's 3 points other than the center core point. So because there's 3 points, now this point that I drew the circle around is in a cluster, and all of the points in that radius are also in that cluster. This is kind of the essence of how Dbscan works. But the reason it's even better than that is because once it's found that a point is in a cluster, so let's draw another circle because this is quite dense. Okay, that was not a circle, but let's pretend it was. So each of these points inside this, well, let's draw a circle around this point right here, that one. Well, that one satisfies these properties too. So this one is also going to have a cluster around it. And these clusters that can form more clusters are called core points. And for each core point, every point within its radius is in the same cluster. And every core point within its radius will also have chain into the same cluster. So all these points will become core points. No matter how many radius I draw, there's going to be a lot of points around them, and you're going to have, these are all core points. Now, when you get to a point like this one right here, let's draw a radius like that. Well, let's expand that to include that point right there. This point does not have 3 or more points. I see 1 and 2. It's a little messy now. It only has 2 other points, and the minimum number of points is 3. But it still can be reached from a core point, meaning it's still in this same cluster. And that means that these are all going to get put into the same cluster like that. Right there. Same thing here. These points are going to all be in a cluster. And this algorithm will keep going until it finds all the points. And it's tested every point. And these noise points, it's going to look at it, it's going to say, there's no points in there. You are nothing. And it's going to ignore it. And that's how it's going to eliminate the noise points. Is it's going to say you're not part of a cluster because you have no points near you. Now, there are really 2 main pitfalls of Dbscan. And one of those is that you have to be able to generate these numbers right here, the min PTS and epsilon, if you where epsilon is the radius. If you don't have much experience with this, or you are unable to come up with these numbers, you're not going to be able to effectively run a Dbscan algorithm. The second problem comes when you have data that is going to have different densities in its clusters. So let's say you have this cluster here, but what if you then also had a much denser cluster as a subset of it, like that? Well, those seem like distinctly different clusters to me. Those are this dense part is very, very dense. And this is something that the Dbscan algorithm can't pick up on. So you're going to have to move to something like maybe a mean shift clustering, or in this case, maybe k-means would be the best clustering algorithm. Although in many cases, this is a better algorithm than k-means. A great example of where this is better than k-means is in a sample where you kind of have a little crescent like that, and then you have another crescent like that. Now I'm just going to draw what these clusters look like instead of just putting points in. So these crescents are intersecting, and what something like k-means is going to do is it'll give you a cluster that's kind of like that and say these are the clusters. But that's really not accurate. The clusters are these long kind of crescent shapes. And that's where Dbscan shines, is in those kind of irregularly shaped but similarly densityed clusters. A third point of where Dbscan fails is in much higher dimensions. Part of the way that Dbscan works is, you generate a radius around your points, and there's this concept of the curse of dimensionality, and it sounds very fun. But really what it's saying is that as you go into a higher dimension, the distance between points is less and less useful as a metric of how dense something is. And the way that's defined is, another fun one, is the volume of a hypersphere over the volume of a hypercube approaches zero as the number of dimensions approaches infinity. Meaning basically that your measurements that we normally would think of and use to measure something don't work in higher dimensions, and there isn't a great way to use the distance in a higher dimension. And because this algorithm is so heavily dependent on distance and this min PTS idea of how many points are near each other, in a higher dimension, these points could be very close to each other in some axes, but very far apart in others, and an algorithm like this just isn't going to pick up on that. So I hope that was helpful as a thorough look into Dbscan. Thank you for listening.